Having observatories, where I had the pleasure of working with him for a couple of years before going to the University of Tampa, where he is now. And today we will talk about his science. So
yeah,
take
thank you very
it.
much. Thanks for coming. So I start talk with this lesson. So this point of an Italian point of this 15th century that represent the state of art of the research on the Milky Way 25 century ago. Okay, that's at that time the sky line was thought to be the drops of milk of the fish breastfeeding by of Hercules by Juno. Okay, so this is not a point. This is actually a plot. Okay. What I'm going to show you today is that the research in Milky Way is still going on. I will show you more updated plot. Okay. Keeping in mind, of course, that maybe in 25 centuries, because my plot will probably look like this one, and we put museum instead of the Science Institute. Anyway, as you see, it's important to study the Milky Way and local surroundings, so the Milky Way systems, that means the galaxy surroundings, and the local group, and so up to one. And we started it many years ago, many centuries ago, and we are keeping doing it so much that in our area, you want to Milky Way, the range from all the range from spectrum, from gamma rays, from size of light in space, up to longer radio waves. In this talk, of course, I won't cover all these things, but I will focus myself only in this range that I here, visible or is beyond, and sticking on these topics. To zoom in this range that I previous you can find a lot of efforts, let's say $1 billion efforts worldwide to study the Milky Way and the local group. These are just a few of the surveys that cover this spectrum range, but even larger. And you are probably familiar with the Dark Energy Survey, but there are some that are past and history and important results now are taking over. There are some that are still ongoing, and there are some that will appear soon. So SST, just quote a few of them, OG, SDSS, and so on. All focused to increase, let's say, our knowledge in our people. Okay. Between them, I will focus mostly on one that I think is relevant for my purpose. Gaia is an ongoing survey, and that will keep on going for still a few years, and has some special interesting point of observations on the fuzzy space. Basically, not only on the photometry or spectroscopy that you are observing, but the goal of this satellite is to study where the stars, where the objects, the galaxy, the asteroids are in a given configuration space, the position part of the space, and where they are going. Okay, so where is pointing a vector, the true velocity vector of that object in the space. Okay, Gaia do not give it exactly this white arrow. Gaia gives you the projections of the unknown velocity vector along the line of sight, Gaia velocity, we will speak about, and orthogonal to that, the orthogonal velocity is described two-program motion in some coordinates. This is a special. This is the reason why Gaia is special. It's the only one that can provide locations, so dynamics and positions, so a map of the fuzzy space, and hence, we'll say, a way to recover, to reverse this projection, that analytically is a projection operator, to reconstruct from the yellow and the green line, the white one. When you have a map on the fuzzy space, you have powerful mathematical tools that allow you to know where the object was in the past, different from where it is now, and as a consequence, where it's going in the future. Okay, that's a dynamic, still dynamic for interest. The second highlight of this satellite, this special survey, is the one that you see here in the right star. So is a full sky survey. There is no point in the survey sky you can have that are not mapped like this satellite. Not mapped all in the same way. There are zones that are observed many more times than others. So if you are lucky that you have your asteroid in one of these zones, you will have very good precision in white arrow. Or a little less in others, okay? And depending, of course, that is kind of low, but here is represented for 7 years, to say theoretical observation. In detail, Gaia, as I said, is a satellite, has been sent a couple of years ago. In numbers, 20 million stars, precision of 1%, a lot of proper motion, radial velocity, distances that I introduced before, tangential speed, astrometric parameter because it has a spectrometer, and that means also stellar effective temperature, like extinctions, and so on. So planets, and also proof of the general relativity for the bending of the light to the massive object we have ourselves, that is the sun. Okay? So it's an important step forward in our understanding on the local group, let's say. And with data release in this scenario plan, so we already have the second data release. The full release will be probably the last one in 2025. It has been extended for a couple of years. What would you like to do with that data in your future? Well, there are a lot of, let's say, challenges that we want to address and research. Of course, the structure definition of the fuzzy space, so how is the shape of let's say, that space that I introduced before, or the most important, the weight of the stellar population, the bar, how they compose the spiral arms, the spiral guidance. So we want to know about the spiral arms. And also, but as a consequence of dynamics from what we do not know or what it is, or we can understand as a consequence. So dark matter, its nature, its distribution, its total amount. And that will give us, when, as I said before, when we know where it is exactly the point of an object in the fuzzy space, it will give you us the possibility to apply the stellar dynamic theory to integrate with time to understand the past evolutions of the object that we want to study. So ways to structure information and the scenario for its evolution and so on. And theory of stability, effects, classic reservoirs, so all the stars forms, die, and all the things like that. Okay, there is a bunch of paper already coming out, so we are of course not waiting already for year 5 to come out. A lot of people are already working on these things. And there are already nice review about interest. That's from the solutional point of view. From the theoretical point of view, I'm very chance. So there's, of course, interest in understanding how to merge together the stellar dynamics, so the descriptions of the fuzzy space, of, let's say, the configuration space and the velocity space that I introduced before can be described technically simplex manifolds, where basically is the Lagrangians of the Hamiltonian that we probably studied at school that better describes the evolution of your system. And that is stellar dynamic theory nowadays, but it was a couple of centuries ago called celestial mechanics, and at the beginning of the past century was analytical dynamics. It's just an evolution of the mathematical technique. And from the other side, there is a theory of stellar populations, stars, balls, light, following its own rules, basically the evolution of stellar structure. And what you want is to merge these theories so that each point in the existence space of the stars, where it is in the, let's say, its density, temperature, positions, and positions because the space merged with merge with this stellar dynamical theory. And that's a way in which, let's say, can be simplified very roughly the goal of a theorist. On top of that, another problem that theorists often face is that unrealistic simplification. I assume that the stellar population is a triangle, the bulge is a cylinder, and the heart is a cube, and I have, of course, a perfect galaxy, right? But not really. But sometimes that's one of the problems. You have to overpass basically symmetry on the mathematical functions that you used. In a single word, we speak about galactic archaeology, the study of the region of evolutions of the Milky Way system, for example. In this talk, I will not speak about the theoretical aspect that I just touched by the previous slide. So the definition of stellar population theory and properly linked with the symmetry require the definition of correct analytical phase space and how they evolve in gravitational fields. That's called physical, you know, probably about gauge theories of phase. Doesn't matter. I will focus on the second aspect, on a tool that I recently developed online that show how this theory is applied and what the results and advantages it can give to you. With the goal to consider the most available up-to-date observational constraints to match the observational data to understand, again, as I said before, where and was in the past the system and where it is evolving. Okay? In a single word, guide exploration synthesis model, GAL model. GAL model is, in 3 single words, what does this modeling do? Is assume a best model available for stellar population theory and stellar dynamics merged together at the best of our present knowledge, say. So for you, it models synthetically a star, a synthetic photometry of a star, a synthetic radial velocity of proper motion. Okay? But you project this synthetic model through some filters that for which you, for example, observe a star basically. And it gives you the possibility to give to have a synthetic catalog of a field of view that you point where you want your virtual telescope. Okay? The background of this model is in a single slide. This is how to put what are a million row codes in a single slide. so it's a kind of a dense slide, but basically that tells you what the model is doing for you. It has based on a few blocks. Okay, synthetic column CMD generator. So you assume a given photometry, take-home photometry, because we are here, you know, you are involved with DSS or whatever. It has a lot of photometric systems. It assumes that your stellar populations has certain given distributions of stars in mass. Okay, that 5 stars in the range of mass, 7 and others, so on. So initial mass functions. It assumes that the stars burn, the gases burn, and the stars more, let's say, evolve even with an assumed star formation history. Okay, so different star formation for the Milky Way disk and for dwarf galaxy, of course. So you can somehow introduce a profile you want and measure this profile. That is enough to generate, to tune a stellar track, to solve the equation of stellar structure and put them in a observable space in column-matic diagrams. So the observable version of the compressor diagram. This is done accounting for the extinction model where we are sitting in a disk of the Milky Way, and so we have extinction in dust, and there is a model that accounts for that. For that stars that you generate, it assign, following a model, it's kinematic. Okay, the model is tuned on observational value of symmetric drift, rotation curve, and they produce a proper motion radial velocity, something that you can directly observe based on gene secretion, let's say. And everything is joined together, but the gravitational potential. Everything that we feel here is due to a gravitational potential that is due to a rotation curve, a function, terminal velocity, rotation curve, and so on. And so on. Basically, if you have an observational constraints that you want to match, you feed your data to the system, and an algorithm, a genetic algorithm, you can use other. I work with genetic algorithms. I work with LOG, that is an acronym for automatic rendering instrument, synthetic model but basically try to fit this system that of course has a lot of parameters on the best match for your observation. Okay? Why this system is important, and what is the advantage of this story with what is available in literature? Well, first of all, it allows you large field of view. Nowadays, cells are large or full sky coverage. Okay, so basically, you can easily deal with column and diagrams that are millions of stars in a single interval of color and magnitude. Okay, so what we are interested is that you want to be able to produce in a single shot billions of stars. Okay, so to produce a rendering on a color magnitude so big is intrinsically difficult because a random generator has to produce number that satisfy distribution function for million of stars. That would take forever. Vice versa, one of the facilities I implemented is a morphing of distribution functions. So basically, automatically the code comes to the distribution functions. If you want the stars, it will sample it from a multidimensional distribution functions. Otherwise, you can immediately have a colorimetric diagrams representative of billions of stars in a single shot. For example, these are, let's say, it is based on a database of pre-counted stellar populations. A simple stellar population is basically a group of stars or variable metallicity of mass at a given position in the Pareto space that are sampled depending on the distribution functions of your galaxy. Here, for example, is of a sphere to produce a color magnitude diagram. This is an example of color magnitude diagram that has 10 to the 6 stars, so millions of stars produced in a fraction of a second for matching an cell with field of view. And probably one of the highest numbers you can imagine. And the reason is that when you want to match an cell catalog, for example, this is an SPSS catalog with 10 to the 6 stars, you have to move these tons of parameters thousands and thousands of times. So you want to generate a million of stars thousands of times to find the best fit. You want to morph analytically distribution functions in a suitable defined space. This is an example of, this is actually an example of the large size of field of view that you can track with Gauss mode. And here it's not a match of the observation. Is a showing where actually the not as symmetric features can be relevant. This is the center of the bulge. You have different bars, so here are very relevant and so on. And here are also relevant because of the presence of spirals. That's because one of the features of the Gauss mode is also that it relaxes symmetry. So if you have a classical description of an asymmetric system, your Newtonian is cyclic in coordinates, so it does not appear in the coordinates, and you can say perfectly, yeah, you know, my system is this, so more or less a spiral. It looks perfectly as it is, right? Well, no, not really. The Gauss mode relax. This is my expression. Relax these assumptions of asymmetry, introducing the azimuthal coordinate, where the sun is indeed placed in a given position outside of the center, and when you observe a star in a given position, it's account for over the density due to the spiral lines, okay? Because we direct the spiral lines. So it's done, of course, to overpass already traduced model available in literature, like Sanson and that work on asymmetric features, and introduce bulge and bar, so a heated bar at the center, and circular bars, and spiral arms. Okay. This is an example of a bulge model. As you see, you have not a symmetric feature. The sun is located in the offset. And over density that are changing depending on which direction you are observing because of the presence of spiral arms, 1, 2, 3 spiral arms. Furthermore, bar, because there's a lot of there's a huge effort to study the central part of the Milky Way, most of all with different surveys. And here is an example, for example, over density in the directions of the peak, the Tampa peaks that you can have study the effect of the bulge observations. That is due to the fact that the bar being tilted offer not a symmetric density field on the left of the center or on the right of the center of the Milky Way. And it is tracked, is traceable also in the radial velocity plane. So radial velocity on positive or negative longitude have different distributions. So predictions of the models that can be observed by nowadays present observations survey like the one that I produced here. Furthermore, regarding spiral arms, one of my favorite topics, spiral arms have the possibility to change the radial, change the circular velocity due to the presence of this over density around them. And so change, for example, the motion of the sun relative to the perfect circular orbit, local sun presence. Or this kind of candy that you see above and below the plane here, or let's say B to the respective galactic center, are the second order moment of the distribution functions, so small ellipse orbitals that can be tracked analytically for the Milky Way plane. That's one of the unique facilities, unique features that are available for that. Furthermore, not trivial to implement a ray trace extinction model, so a way to account for the extinction due to the not axisymmetric presence of gas distributions. The gas mostly stay around, for example, spiral arms, so the density is clearly totally not symmetric, and the effects are now visible in observations. This is an example of double exponential distributions, so fully analytically distribution of extinctions, and that's the result obtained with the spiral arm distributed. So again, an observable visible difference between the two models due to the implementations and not asymmetries. Not only these things, if you, for example, do not care at all about what I said so far because we do not work on the Milky Way. Let's say the Milky Way is produced spun, and you are interested to study something outside the Milky Way. Let's say I want to study CNA, so an external elliptical galaxy 4 megaparsec away from when you get an observation about this is you see that there are contaminations along your field of view that represents the Milky Way, but you are interested only in the external galaxy. So you can use GAL mode as other systems similar to predict where is the Milky Way disturbing your observations and how to get rid of it. Okay, this is the same obtained with a different model available. Here you can propose a situation where GAL is better. Because I propose GAL, of course, I suggest everybody to test all the models available. They are just so but is unique in other situations where there are other models that can test. For example, open cluster radiation system that bonds and stellar cluster in spiral arms. So an observation HST photometry of an open cluster cannot be treated with if you do not account for the spiral arm, like in the case for Gregor. But if you add the spiral arm distributions, you can detect the observations and the Milky Way to see which stars are contaminated. Okay. in the middle. So for example, here Milky Way, here the cluster. Where are the stars contaminating or the Milky Way, your cluster of stars? Well, you can gamma beacon estimation. Okay. Another interesting feature is, of course, if you are interested by itself to external galaxy, let's suppose M31, for example. Gamma has already a modality to model external galaxies that are readily available on, for example, M31, but to work on and just later let's probably of galaxies, and the discussion is the same. If I relax axis symmetry for my systems, well, the most obvious thing is to say, well, I can move the sun wherever I want. Why not to move the sun outside my system and look for my system from far away? That's how it works. Basically, gamma allows you to move a galaxy wherever you want inside the local group, limited to the local group, because there's not cosmological corrections for the moment. It's a redshift. The radial velocity as well, the diagram, and so you can model, for example, M31. How to, let's say, this system by has, of course, its own velocity in a given reference frame, supergalactic, for example. So how to have the proper motion radial velocity of systems that are far away from our Milky Way, and so that can be detected observationally. Well, for example, in this case for M31, I added by default, but you can change it. I add by default the radial velocity, the proper motions, the radial velocity is but proper motion can come from the integration, not the integration of an orbit, but it's equivalent. The integrations of the functions that I told you at the beginning that describe the systems in the symplectic manifolds, the Hamiltonian or the Lagrangians. This integral is called reductions. The minimizations of this integral is equivalent to the orbit without asking you to put as initial conditions some velocity. So basically, the proper motions are added with a sophisticated technique that account for the evolutions of the systems, not only in M31 on Milky Way, but also the one containing 90% of the mass around the local group. Hard technique, but it is so far the only way to do it. Proper motion are, of course, coming also in the future for maybe local group of galaxies. So them. And finally, another experimental feature of this toy is that once you have perfectly matched your observations of a dwarf galaxy, okay? Once you have in perfect CMD matching, so a perfect radial velocity matching, if you have information, maybe that's also the case, and you have taken away the Milky Way contamination, you can say, well, what does happen if I have time evolution? If I have my time evolution constraint generator or say integrator gadget or whatever software you use. Galmod, for the model that best fit your taste, generated semi-equilibrium initial conditions of the galaxy that can be fitted inside an embodied integrator to see if it evolves the system as you like. Okay, so can generate initial conditions for spiral galaxy, black galaxy, to be put inside the over density of dark matter or cosmological simulation rather than a single model integrations of the system. Okay? This is an example done for a dwarf galaxy, Carina, where let's say the system has been evolved according to the growing mass of the Milky Way and dynamical frictions, and for different starting model. And as you see, this is the time evolution that was used, was achieved in, I guess, with gadget, where the initial condition on GAD model are, and the integration is done backward. So, of course, there's a high probability that you know where is the system now because you observe it. Obvious. But there are also higher probability for the system to be in certain place of the local group positions, okay, in the past. So Carina has some bars of star formation that match that age, that particular age. So you can ask yourself when this pericenter passage match better the star formation burst of Carina. So just to give an example of that what can be explored. To conclude, is everything, do you have to pay for everything? No, it's coming to you everything for free. So, it's available through a web page, interactions. You do not download or install the code. It is a cloud computing system. Basically, you insert your parameter and this toy sends you home the results. As I said before, in 2 slides to say what is doing, there's a design correlation with the company, with a private company. And basically you send your request to a server that let's say, run a simulation for you. And when it's over, it sends you an email where you are informed that the simulation is over and then you can download the simulations, okay? In a single slide. There's a word behind these things, and there's a company that handles these cloud computing systems, okay? Because it's a parallel and so on. Compare with the literature, I did better because it's the best because I arrived later, right? So I learned from who was before me, and I saw where they got improved, and I did better because I started from there on, right? So in one shot you can see some facilities that government checks, some others from the popular presence model, that is historically the most important one. There has been improvement of the possibility to have full sky, because as I told you, survey are almost full sky nowadays. There's possibility to include a bar, because there's a bar at the center of every spiral, or not every spiral, I'm wrong what I said, but a lot of spirals. There's possibility to have an extinction map, spiral lamps. There's possible to produce external object and initial condition protocol simulations. GAL model is not as a lot of information system gets good for that things, and the system is fully symmetric. There's no extinctions, but it's missing of the consistency that the gravitational correlation, the Poisson solver integrator provide. And work in progress, as I said, whatever we do now with, for example, Gaia data will be probably cancelled by the next Gaia data release, because the results that you can achieve with the full data release, especially with the release that provide you extinction, is clearly better than what we can do now. For example, supplying the data with the mass corrections and so on. So, of course, my goal is to study spiral arms. I already have some fits available, but not published yet. And with that Gaia data release 3, probably there is spiral arms, so there you have a system that is asymmetric, can be prepared to produce spiral, to produce stability, and as a consequence, of course, to detect, to understand the Milky Way potential. The future is wonderful, because there is not only Gaia, but we will have a lot of survey that will and facilities that will improve our understanding of the local group. So, in a summary, I don't know when so, importance of the Milky Way, because it's our system. It's so close that we can have such detailed information that we cannot have outside. We're going to have to integrate photometry, we cannot have for external objects. So it's a perfect laboratory where you can then export the theory of spiral arms, for example, to other systems. There are theory that has to be advanced at the same terms of exclusively theoretical frameworks where you can handle the equations in a better way. GAL model is this emerging platform that gives you this mock catalog that you can play with, and there is not only me, but people that work on it, and that's why I cover very different topics, even my expertise too. And so you can use it, and of course machine learning is the next step for the use of these tools because they require a lot of parameters to be tuned, and clearly not everything is visible with our eyes. So the help of, let's say, machine learning or general intelligence machine learning is terms that cover with an umbrella a lot of techniques, but we say that's probably the next steps for what